Thank you very much. Thank you very much for organizers, for organizing this and for having me speak. Yeah, so I've long been very interested in Alain's and her collaborators' work on arithmetic local systems. But when I tried starting to understand what I'll talk about, the topic I'll talk about, I've discovered for myself Alain's work on secondary characteristic classes. And so yeah, I was delighted, and I'll try to show how one of her results from back then was kind of clarifying for what I'll talk about. And so yeah, I'm very grateful to Alain for all of her mathematics, of which I only know a small part so far. So what I'll talk about is all joint work in progress with Lue Pan. And it's so it's a story about secondary characteristic classes, and Dustin talked about them over the complex numbers on Tuesday. So let me very briefly recall what was the just the shape of this theory. So if you had a space, well, let's say a smooth manifold, but you can make it much more general. And you had a complex local system on it. Let's say L was a C local system. Say a frank N. And let's say that my manifold was connected, so it's the same as the data of a representation of the fundamental group into GLNC. Then a conjugacy class of that. Then, well, given such a data, you can pull back cohomology classes of GLNC to the cohomology of M. And Dustin explained that it's especially interesting if you choose these coefficients equal to C mod Z. So in every odd degree, let me consider the cohomology of the, well, let me just write it even more directly, that you can just consider the group cohomology of GLNC, simply viewed as an abstract group. And let me emphasize that the topology here plays no role. So just this viewed as a discrete group. If I consider this with coefficients in C mod Z, then there is a pullback map. So if I know this by rho L, pullback under this map into the cohomology of my space. And the key result was that the point is that now in this group there is a particular interesting class, which I think usually called Ci hat. And so whenever you have such a class, then for every local system, so this class does not depend on any of the choices, it's chosen once and for all. So you get a natural class in here, which now is an invariant of the local system. And so this is what's sometimes called Chern-Simons class. And so this was a secondary characteristic class, and it was secondary to the actual Chern classes. And so the key compatibility with Chern classes was that now if you were to consider the long exact sequence of cohomology, where cohomology with C mod Z coefficients maps to the cohomology with Z coefficients in the next degree. So this is a part of the long exact sequence arising from the short exact sequence of abelian groups. Then if you were to map this characteristic class of my local system in odd degree to this even degree, then the key claim was that it would get mapped to the usual Ive Chern class of the associated bundle. So let me just denote this associated bundle as L tensor over the constant sheaf with the structure sheaf, well, perhaps complexified. So I'm just saying whenever I have a C local system on a space, I can cook out the vector bundle out of it, because the local system is defined using locally constant transition functions, but equal they're continuous functions, so I can glue them into a bundle. And so the key property of these secondary characteristic classes was that they recover Chern classes of the local system, of the bundle associated to the local system. And Reznikov witnessed the fact that these classes, they're a torsion, so they died canonically if you go to complex numbers, but well, they die somehow if you just invert, if you just go to rational coefficients. And so this is the package. So this is the key invariant which you attach to a local system. And what I'll try to talk about will be a p-adic analog of this story. But before I go there, let me state a couple of results about these classes over complex numbers, which will be motivating for what I'll say. So Dustin explained that these classes are very interesting, say, if you look at them in topological situations, such as these hyperbolic free manifolds. And let me, since I'm going to go to some p-adic story, it will be, everything will take place in algebraic geometry. So let me remind you how these classes look like if you work in algebraic geometry. And so there are two results. So the first of them is due to Reznikov, which says that if you now work not in an arbitrary space, but on a smooth projective algebraic variety, then the classes which you'll get will not be very interesting rationally. So let's say that L was any local system. Then the classes which you get in the cohomology of just a singular cohomology of your variety, they're all torsion for I larger than 1. So torsion meaning they die if you go to this group tensor Q, which is just C mod Q. So this is, it would not be reasonable to expect this for I equal to 1, because as for I equal to 1, as Dustin explained, this characteristic class is just equivalent to the data of the determinant of the local system, and that might have an infinite order. But for all higher classes, there are actually 0 on compact algebraic varieties. Oh, sorry, 0 rationally. This torsion might still be interesting. And what's somehow even maybe more relevant for kind of what I'll talk about is the following theorem of Kevin Carlette and Alain. And somehow here, what will be, it will now be a more general type of base, but a more special type of a local system. And so let me just, for simplicity, assume that my base is still an algebraic variety, even though it's not clear. Sorry,
just a quick question. So this doesn't hold for compact manifolds, right? I mean,
right, it holds for compact Keller manifolds, but it doesn't hold for arbitrary compact manifolds.
Okay.
As Dustin demonstrated with this hyperbolic free manifold example, which could have been compact. Okay. So let me just, for simplicity, assume that my base is still an algebraic variety. That's not so crucial, but now it doesn't have to be compact. So smooth algebraic variety. But now let me assume that my local system is special, in that L was actually a polarizable Q variation of Hodge structures. So kind of a key example is that there was a local system of cohomology of a family of varieties for some smooth proper morphism. Okay, so this is a Q local system, and I claim that, so the claim is that then if you consider the associated complex local system, then all of these classes will be torsion. So then the secondary characteristic classes of L complexified they will be torsion in all degrees. Right? So even when I is equal to 1. And so so this is right, so somehow the upshot of these two results that I'd like to take right now is that it seems that at least if you're considering these classes in algebraic geometry, they seem to be giving, so either in a situation where your base is compact algebraic, or if your local system was coming from geometry, then what you're getting was trivial rationally. So now let me move to the p-adic aspects of things, and but it will be very helpful to keep in mind this complex story for comparison. Right? So let me fix a prime number. And now I'll be in the setting of algebraic geometry, well, until the very end where I'll have to move to kind of analytic geometry, but still now there are no complex numbers immediately. So let me assume that I have an arbitrary scheme, and let me just for psychological comfort assume that P is inverted on it. And so suppose I have this time a ZP local system on it. So suppose that L is an étale ZP local system. So as before, this is just the data of this local system is the same as the data of a representation of the fundamental group. And let me assume that my scheme was connected for that. So it's the same as the conjugacy classes of homomorphism from the fundamental group to GLN ZP. Well, if n was the rank. So this is should just be a continuous homomorphism of profinite groups. Well, up to conjugacy. And so whenever I have such a homomorphism, then as before, I could just try to play the very same game. So I could pull back cohomology classes of this group to get cohomology classes on X. So here there's a slight, I think, at the first sight there's a difference here in that the topology in this group now does matter because this is really a continuous homomorphism. But still the algebraic group structure in GLN does not matter at all. So it's natural to consider continuous cohomology of the group GLN of ZP for this. And well, I'm free to choose any coefficients, and it's most interesting when coefficients involve the same prime number as this number p. And it's certainly very interesting to consider this with integral coefficients, and I think Dustin has some very interesting results about this, but I don't have anything non-trivial to say about integral coefficients, so I'll just resort to using rational coefficients. So let me use QP. Then, well, if I have a cohomology class of this group, I can pull it back to that group to cohomology of this profinite group phi 1. And then, as always, there is a natural map from cohomology of fundamental group to the cohomology of the whole space. Right, because this is cohomology on the side of finite étale covers. This is cohomology on the side of all étale covers. And so let me denote this composite map by rho L pullback. So where rho L was this homomorphism attached to L. Okay, so I've got this map which is very similar to what I had over complex numbers. Now, over complex numbers, the key was to kind of pin down some interesting universal classes which you'll then be pulling back. And so I should also choose which classes here in this universal case are going to serve as my characteristic classes. And it turns out that here I can actually completely compute this group. And the answer is, well, in a way more tame. So this is a profinite, this is a p-adic Lie group, in fact. And so if I replace it by an open subgroup, then the induced map on cohomology will be an injection. So I could say that it doesn't change much if I replace it by an open subgroup. So if there's some invariant of a p-adic Lie group, which really seems to only depend on arbitrarily small open subgroup, and it's not surprising that it's actually expressed in terms of the Lie algebra of GLN. So it's a computation of Lazar that this is with rational coefficients identified with the Lie algebraic homology of the Lie algebra GLN, taken with QP coefficients as well. Now, technically, it's still you have to remember a little bit more than just the Lie algebra, because there's a priori a residual smooth action of this group, and so I have to take invariance for it. But in this particular case, it turns out to not matter, so this action is already trivial. And so this is actually just the cohomology of this Lie algebra. And well, if you have a reductive algebraic group in characteristic 0, then cohomology of its Lie algebra is the same as just the cohomology of the underlying topological space of the complex points of the group. And so cohomology of GLN, we know that. So that's freely generated by several classes of non-degrees. So this comes out to be equal to the free, well, exterior algebra on classes L1, which I'll denote by these letters, and the degree of the ith class is 2i minus 1. So numerologically, we also constructed classes in all odd degrees, well, for a given n up to n. And so now, well, having done this computation, I can just define characteristic classes of local systems. So let me introduce this definition. So I think this may be the first time I saw it appear in literature is in a paper by George Pappas, and he really emphasized the analog of the analogy between these classes, which I'm about to define, and these Chern-Simons classes. So I'll call them Lazar classes of my local system L are defined as images of these universal classes under this classifying map. So note an Li of L. So now they live, these lived in odd degree cohomology of this group, and so they map to odd degree étale cohomology of this space, of my scheme.
Can you say what we obtain integrally on the left? So when QP is the...
Right, this is a very good question. I don't know if there is a very canonical, so of course you can make them integral by introducing enough, by multiplying them by a large power of p. I don't know if there is a very canonical choice of an integral class.
Can you view that in terms of Archie cohomology of the algebraic group GLN over FP or whatever base?
Oh yeah, yes. Certainly. So, well, at least rationally, certainly.
Yeah.
Right. So this was the topic of Lars's talk, I think, right? Because this, this is well, somehow you see this is exterior algebra on some elements, and well, this is in fact. This is in fact a Hopf algebra, and it's exterior algebra on the continuous K theory of this ring ZP, which in turn rationally can be related to cyclic homology, rather. Yeah, Mark, it's a very interesting question what happened integrally. I don't know how to think of these classes integrally, but yeah, Dustin has some way of thinking about some characteristic classes integrally.
No, I mean if you replace like ZP by ZP bar, then there's just a canonical integral refinement.
Ah, right. This is one, right.
And that so these are and those are pulled back.
Right. Right. Oh yes, right. Yes. And but those will still be with coefficients in QP or with in this larger.
Yeah, no, they'll be integral. But then if you tensor with Q.
Oh, sorry, what was ZP I meant? Or?
No, they actually extend to QP bar.
Oh, okay.
Yeah.
Okay. Right. Thank you. Yeah, but all the actual proofs will use rational p-adic Hodge theories. So I'm only able to say something about them rationally. Right? Are there any questions about other questions about the definition of the classes?
Sorry, I have a silly question. So why this is not like something like homotopy fixed point?
What was this homotopy fixed point?
You are saying groups. So
yes. So it's a smooth action now. So it actually factors through a finite group, and so this is a rational vector space.
Oh, okay.
Right. So all the kind of group homology of G1 of ZP got absorbed into this Lie algebraic homology. All the higher homology. Okay. So, okay, what can you say about these classes? And given that, right, so now it's all happening in algebraic geometry, but now these analogous complex classes, there were torsion in algebraic geometry, at least in some of these cases. So let's just consider first the simplest example. Suppose that my degree is 1. Here, Dustin explained that over complex numbers, these classes, they just recover the determinant of the local system, and the same happens here. So for I equal to 1, I'm telling you that there is some natural class in H1 with QP coefficients. So I claim that it's completely recovered by the determinant. So I can view the determinant, of my local system as it's a homomorphism from the fundamental group to ZP cross. So I can view it as a cohomology class of my X with coefficients in ZP cross. And the claim, well, there is a p-adic logarithm map, and the claim is that this is just equal to the p-adic logarithm of the determinant. This basically amounts to the fact that this class in degree 1, class in H1 of G1 of ZP, this was just a homomorphism from G1 of ZP to QP, and this was logarithm of the determinant. Right? So in degree 1, this is an understandable class. But something more sophisticated will happen for higher degrees. And
I'm sorry, why are there no Tate twists?
Right, very good question. So there will be no Tate twists, right? So, well, because this was just a homomorphism, which was, this was literally already the fundamental group of my scheme. And well, even if it was over some algebraic closure where there is some Galois action, it would be equivariant, well, right. It's Galois equivariant as written. So, right, this is an important feature. The Tate twists will appear, but they're not there yet. Right, so what happens for these higher classes? Somehow it will soon transpire that this is actually most interesting if you work with varieties over some arithmetically interesting fields. So let's say over number fields, or at least over p-adic fields. And so let me put myself in a situation where my X lives over a number field. And let's say it was smooth. So F is a number field. So now let's just say I happen to have a local system on this X. So now it's a representation of the arithmetic fundamental group, and those things are kind of much more sparse than representations of the topological fundamental group of a manifold. And so the main source of examples of such things is in fact the cohomology of family of varieties. So for example, you can think that the cell was cohomology of some family. Let's say smooth proper just to make it a local system. Right, and this family was defined over the same field F, so the local system of the Petrov cohomology is defined over F. And well, you won't lose much if you just assume for all of what I will be saying, or almost all of it, that this is a local system that we're dealing with. So suppose you have such a local system, then this construction gives you characteristic classes. So where do they live? Well, they live, even though I said that my variety lives over a number field, all this discussion was absolute. There was no base over which X lived. It didn't matter. So now I get classes in absolute adult cohomology of just my variety X considered as an absolute scheme. So this is the absolute adult cohomology with trivial coefficients. But let's just to get oriented, let's first map this to the geometric adult cohomology and see what happens. So because previously our characteristic classes did live just in singular cohomology. So the analog of singular cohomology would be cohomology of the base change to the algebraic closure. But well, this map, just by functionality, it has to factor through Galois invariance in here, right? Because this was defined over a field F. So this lands in Galois invariance, where this is just my notation for the Galois group. But since my variety is smooth, this is actually 0, well, when I is positive, by weight reasons. So by weight conjectures, for instance. Right, the trivial character cannot appear in higher degree cohomology. So this group is actually 0. So my classes, if I consider them in the geometric setting, well, if they came from a local system at least defined over F, then they would be 0 in geometric cohomology. And I'd like to think of this as an analog of this result, which says that in this setting, if my local system had this additional structure, in this case it was this polarization, and here it was this Galois, it was the being defined over number field, then the classes which you get in the geometric cohomology are 0. Right? But still, well, this group is potentially much larger, so I have some classes here. Right? So how does this group look like? Well, I can access it, say, by the Hodge-Schulze sequence. So it's a combination of cohomology of X over F bar, and then cohomology of the Galois group acting on that geometric cohomology. So since this group vanished, there was a residual map to the first cohomology of the Galois group with coefficients in the absolute, sorry, in the cohomology of base change of my variety to the algebraic closure. And now the degree is 1 smaller than the degree in which my classes lived. So this wave starting from a local system, we produced some classes in the Galois cohomology of the Galois group of my number field with these coefficients. All right, and we could try to see what these classes are. So this will be the question which I'll try to partially answer. But are there any questions about the setup? Right. So here is what can be said about these classes. Again, so far, nothing really indicates that they're often non-zero. So again, any kind of real computation that I know how to do, it happens over p-adic numbers, and it uses p-adic Hodge theory. So I'll only be able to say something directly about the restriction of these classes to the decomposition group of a place set P, where P is the same number. So here's what you can prove. So let me put myself in a fairly restricted setting, and then hopefully when I'll explain the proof, it will be clear why I had to do that. And I hope that the general story might still be understood by similar methods, but there are some things which are missing. So let me say that I have a variety which now lives over QP. And let's say that it was a smooth projective variety. Oh, proper of some dimension. And let me assume that it's geometrically connected, so just one geometric connected component of some dimension n. And so suppose I had a local system, which was now not completely arbitrary, but I'll assume that it's Hodge state. Don't call
was
it.
the rank of your local
Right.
system.
Yeah. Okay. Great. Okay. I have.
D.
Oh, you'll see why it's a bad idea, but we'll see. Yeah. Thank you.
R for the rank then.
Well, let me try to salvage it from here. All right. Thank you. Right. Somehow, the rank of the local system will not make an explicit appearance because kind of, as Dustin explained, all these invariants are stable. So if you view this as a local system with a larger rank by adding a bunch of copies of the trivial local system, these invariants are still recoverable. Right. But thank you. Yeah. So suppose this was a Hodge state ZP local system. Let me, before even stating the theorem, let me briefly remind you here how to think about these Hodge state local systems. So it's one of the analogs in p-adic Hodge theory of a notion of a variation of Hodge structures. And so in particular, it's a gadget to which you can attach a bundle called d Hodge state of L, which is a graded Higgs bundle. So it's a direct sum of several graded pieces indexed by integers. And there's also a Higgs field which shifts the grading exactly as in complex Hodge structures, complex variations of Hodge structures. The Higgs field will not be explicitly important for me, so I'll not write it here. And so it's a class of local systems to which you can attach Higgs bundles and of this special form. And all local systems of geometric origin, they do fall in this class. So for example, if L was the relative cohomology in some degree of a family of varieties. Oh, sorry, yeah, this is why I didn't want to use D. Let's call it M. So if this was a relative cohomology of some morphism, then this d Hodge state is what you think it is. It's the relative Hodge cohomology. Yes, please.
Does it shift to m minus 1 or to plus 1?
M goes to m minus 1.
Great.
So it's kind of
just like in
exactly. Yeah, right. So here it's the usual structure. It's the Gadaira-Spencer class displacing the Hodge filtration by 1. Yeah, exactly. Right. Right. So this is you wouldn't lose anything at least for here if you just assume that this was my example. This is just a general p-adic Hodge theoretic condition. So let me assume that I'm in this setting. This was my reminder of what this looked like. So then what's the answer for these classes? And I assumed this restrictive condition because I'll only be able to say something about the top degree class, which in this case, it will have index d plus 1. So the Lazar class of this local system, it lives in cohomology in degree 2d plus 1. Now, so you see this is 1 degree larger than the geometric cohomological dimension of X. So if you run the Hochschild spectral sequence, there will be a natural isomorphism between this and cohomology of the Galois group of QP. First cohomology with coefficients in top degree cohomology of this variety. Okay, now what is this cohomology group? Well, that's the top cohomology of my variety with geometrically connected. So this is just the minus d Tate twist. And so this number can in fact be, so this group can in fact be canonically identified, say, by a dual to the Bloch-Kato exponential with QP. So in this case, my class is naturally a p-adic number. And it turned out that there is the following expression for this class. So it's equal to the following sum. I'll write down that sum, and then I'll say in what sense it's an element of QP. So it's a sum over all the m which appear here in this grading so in front there is a constant, which in this case is d factorial. So it will be a weighted sum. My weights will be the integer appearing in my grading of the top Chern character of the graded pieces of this bundle. Now, what is this? So this is a vector bundle in my variety, on my d-dimensional variety. I take its Chern character, I take its degree d component. So this is now just a rational number, because it's a class of a cycle of dimension 0. And then I even multiplied on the front by d factorial, so it's actually an integer now. And then I summed up those integers. So this is actually just an integer, and well, I view it as an element in QP. So this a priori p-adic number turns out to be that integer. Okay. All right. So
here you assume geometrically connected X.
yes, absolutely, for this isomorphism to be true. Right. But I mean, these are all rational computations, so I can extend the base field by a finite extension. I wouldn't lose the information about the classes if I really wanted to. Yeah. Right. So in general, there is a certain weaker, right? So there is for classes in arbitrary degree, there is certain weaker information we can brief, but right, we can't quite compute these classes completely yet. All right. So it turns out that these classes now are not zero, and they're related to this Hodge theoretic invariant. And right, so let me make a couple of remarks about this result. So let me make the first one orally, which is really not a rigorous statement, but I'd be very. I don't know what's the analog of this result over complex numbers. Oh, yeah, please.
I mean, one analog, very briefly, but I don't want to take your time, but when you go from the Rham to Higgs via Simpson, via Carlos, so now it is a case that you on the Higgs side you can always deform to complex variation of Hodge structure. So that for the topological Chern classes, you don't change the Chern classes along this way. But now you have C variation for structure. So then the Chern classes are the same as the initial as the Rham associated to the variation of structure. But now it is presented as a sum of Chern classes of the created pieces.
Right, but here it's weighted, right?
Yeah, but you take the Chern character, so I would think.
Right. So it's I see what you're saying. Right. I've right. Right. Thank you. Yes. I've right. I've right. So maybe no. Please. That's the point. So right, maybe one remark is that if I didn't have this weight in front, if I just summed up the Chern characters is the sum of a bundle. It's the Chern character it's the sum of Chern characters, and in fact, just the direct sum of all these bundles without weights, that would be a bundle. It would be associated graded of a bundle with a flat connection. So its Chern character would be 0. So this only kind of becomes non-zero because of this weight in front.
Because you take an Artin-Ries.
Right.
It's an Artin-Ries construction.
Yeah.
I have to complete what I said.
Right.
Just for the interruption.
No.
Yeah.
Yes. Right. Great. So now, let me say that in broad terms, it's not, well, this invariant which is written here, it's completely recovered from the local system. By definition, there is some p-adic procedure. So really, this bundle, it's obtained from L by a certain p-adic comparison isomorphism, and so it kind of remembers. So if you think of L as of a variation of Galois representations, this p-adic Galois representations, this d-Hodge state of L remembers how their p-adic periods vary. And but now what this says is that this particular kind of combination of numerical invariants of these graded pieces is recovered from a local system by this kind of more direct procedure. And you can reap some benefits from this, now even if you're not over a p-adic field. So let me just state this briefly as a corollary to give you a flavor. So, yeah, please.
I mean, somehow, I wonder how all these invariants, is determined up to isogeny of L or something.
Whether it's determined, yeah. I think if you replace L by an exogenous local system, it will be the same. Yeah.
Okay.
Yeah. Great. Yeah, actually, right. I don't know if they literally only depend on the QP local system, on the QP representation, but right.
I think that's true.
Even over ZP, right?
What's that?
Even over ZP, right?
Yeah.
Oh, okay, great. Maybe I'll ask you this. Okay, great. Then it's tautologically answer is yes to Johan's question.
Yeah, just because in complex case it looks like it's completely rational. I mean, you don't have an integral information that's interfering with invariants. So
well, there are no integral information on coefficients, maybe, but right.
And small question.
Yeah.
So if we know X is coming from the local system and X are all defined over number ring or some more part, do you have some constraint?
This was going to be my next remark. Thank you. So I'm glad that I didn't make it. So let me make a very let me put myself in a very specific setting. You can guess how this remark will be made more generally. Let me assume that I live over an imaginary quadratic field. Sorry, but there are probably many things to say about number fields. I'll say one thing, and it's not quite what you're asking for. Please ask again. So suppose I'm an imaginary quadratic field, so degree 2 imaginary extension. Let me assume that P splits in this extension. So the ideal P, it's a product of two different prime ideals in OF. So now let's say that now my X lives over F, and it's smooth proper of dimension T as before. And so the result I will state, it will be partially conditional, and so let me assume the following conjecture in Galois homology. Assume Schneider's conjecture. Which says that if I computed second cohomology of the Galois group of this number field with coefficients in QP mod ZP twisted by the inverse of this D, then this will be 0. So my understanding is that this is a general open, but for instance, for a given F and given P, it's true when D is large enough. Okay. So here is the corollary of the theorem, and let me emphasize it's conditional on this. So suppose I had a local system on X. So ZP local system on this X. And so it was a local system over a number field, but now there are two ways to make it into a p-adic local system, because this is a degree 2 extension and P splits, so there are two different embeddings of F into QP. And so let me suppose that for both of them, if I restrict it either to the completion at V1 or at V2, sorry, L restricted to that. Suppose that they're both Hodge state local systems. But I want to emphasize that a priori these are kind of distinct conditions, because from the point of view of p-adic, from the point of view of p-adic geometry, these are two kind of different varieties over QP. And even if I assume that, then it does happen that, say, these have different Hodge state weights, right? So they're not obviously directly related to p-adic geometry, but so far the information about their relation is that they came from a global local system. But then, assuming this vanishing, it follows from this formula that the right-hand side of the formula actually does not depend on which place you choose. So the sum of these funny Chern characters it's which is just a rational number now. This is sorry, of L. To talk about d Hodge state, I have to be over a p-adic field, so this means X restricted to a completion of F at a p-adic place, so I is either 1 or 2, so this is independent of I being 1 or 2. Even though, like, a priori, so these could have been completely different p-adic local systems. And so it's a type of result which would be clear if my local system was of geometric origin. Let me make this remark. Or specifically, not just of geometric origin, but really motivic, so cut out in the cohomology of a variety by a cycle, not just a subquotient. So this is true if L is motivic. So this will be completely right. Basically, this is in general, this is a consequence of Hodge symmetry, because the complex conjugation switches these two places. So if you write it out, but now I'm claiming that in general, well, you expect a much finer relation between even these bundles, not just their numerical invariants, but at least from this discussion of characteristic classes, you can deduce unconditionally, well, modulo this that this numerical invariant looks as if the local system was of geometric origin.
And Sasha, if you had, do you know whether, do you have an example where it is Hodge at one place, one split place, but not at the conjugate place, and then it is not independent. Do you have an example where it's not true? You don't assume that it's Hodge in both places.
Right. So there are certainly such examples. I think even you can have a character of the Galois group, which is Hodge at one place but not at the other. Right, because here I think the group of Hecke characters has rank 2. So you see this formula, it kind of depends on the Hodge state weights. And so even if it was not Hodge state, it's always Hodge state in the generalized sense, in this, with weights which are now p-adic numbers. And so if you wrote this with weights being p-adic numbers, it would always be true. Okay. So even if it's not Hodge state at one place, you still get some equality, and so you can measure it.
Excuse me. Please. How distinguish imaginary and real quadratic fields?
Right. So I think if it was a real quadratic field, then so here kind of what appears here. So what I'm claiming here is the fact that I have for these two places I have their Galois homology classes, and the extra information which I use is that they came from a global Galois homology class. So I'm studying the map from this global Galois homology to the local homology. And the claim is that in the imaginary quadratic field case, this map is not surjective. It's a map from one-dimensional space to a two-dimensional space. But in the real quadratic case, it's actually a map from two-dimensional space to a two-dimensional space. So coming from a global class is not a constraint. But yet, to know that it's exactly one-dimensional, I think I have to assume this conjecture. Right. Okay. So let me, in the remaining time, say something about the proof of this theorem and where this comes from. Okay, so somehow Dustin's lecture was called secondary characteristic classes or secondary invariants of local systems, and it was clear what was secondary about them. They were secondary to Chern classes. But the way I defined these Lazare classes, it wasn't immediately clear if they were secondary to anything. And somehow the key to understanding this turns out to realize what they're secondary to. And it turns out that that primary thing is still Chern classes, but Chern classes of a slightly larger class of objects than just vector bundles. And so let me introduce Chern classes of pro-étale vector bundles. Let me briefly recall what pro-étale vector bundles are. This is now really a p-adic analytic notion. So let me assume that now, sorry, I'm switching the meaning of my X all the time, but hopefully at any given point it's understandable, but please ask me if it's not. So let me now assume that I live kind of in analytic geometry, and let me say that X was a rigid analytic variety over QP.
So before going on, so you previously theorem, I'm not sure whether, this theorem, yes. This theorem, is it also true for rigid analytic? I mean,
oh, yes, absolutely. Yeah. Right. And it will be proven through analytification. Yeah. So let me assume that X is rigid analytic variety in application. Well, yeah, you can assume that it was an analytification of the algebraic variety we actually cared about. So then to this you can attach its pro-étale site. And so let me not define this completely, but basically it's an enlargement of étale site. And so let me just say that its objects are spaces U map into X, so generated by étale covers, and inverse limits of towers of finite étale covers. So what is the point of this? So the point is that here over complex numbers, given a local system, I was able to attach to it a vector bundle. And what was crucial for it was that my local system was locally on my space. It was trivial because my space was locally contractible. And if you work with étale local systems on an algebraic variety, those are not locally contractible for the étale topology, right? There's not a single cover which makes them trivial. But now here, this is just a topology where they do become locally, where the local systems at least become locally trivial. And this allows me to look at this larger category of pro-étale vector bundles. So this is just locally free sheaves on this side of modules over the structure sheaf. And I'll note the structure sheaf by OX hat, and hat here is to emphasize that it's p-adically completed in that if I take an object which is an infinite inverse limit of finite cell covers, the structure sheaf of that limit is not just a direct limit of structure sheaves of finite levels, but really the p-adic completion of that in the appropriate sense. Right? So I look at these vector bundles, and what is this category? So let me just give two examples of objects there. So if you had a classical vector bundle, then you do get a pro-étale vector bundle. So vector bundle just on the analytic side of X. Let me emphasize, basically, writing X analytic. So let me just introduce notation for this function. So this pro-étale site, it maps to just the analytic site. This map is usually called nu. It's basically just recording the fact that this site has more objects than that one. So all analytic covers are included here. So I can pull back bundles. And let me use this notation for the pro-étale bundles. Okay, so here I'm not really using these inverse limit of finite L covers already, and a L cover is sufficient to trivialize such a bundle. But then what's new is that now I can also view local systems in this category. So let's say if I had a ZP local system. Well, again, next. I can also map them to this category. So L would be mapping to L terms of the structure sheaf, where here I view it as I view my local system as a sheaf on the pro-étale site, living over the sheaf ZP, which is just arising from the topological ring ZP. And now the key point is that this formula does give me a vector bundle exactly by this property that I described before, that this L was a locally constant sheaf on this site. Okay. Right, so it's just in my notation. So this is just to emphasize that. So here you might have some object. So let me write a formula. I'll have to explain in what category all the objects live for it to make sense, but maybe I'll not do that, but I'll just write a formula. And I'm just saying that you might have some tower of finite L covers of growing degree. And all these maybe are rigid analytic varieties. And so if I took their inverse limit, so at least if all of these were affines, then I'd like to declare the value of the structure sheaf here to not just be, so let's say they're affinoid. In algebraic geometry, I would have just taken the direct limit of functions on all these UIs. But here I would take its p-adic completion, where I have to explain what's the p-adic topology in that. So I mean, all of this story I could have done in algebraic geometry, but it will be very crucial for me that it's all happening in p-adic geometry, because I really use elements in the structure sheaf which don't come from finite levels for some of the constructions.
Just a quick question. So I remember there's some subtlety about the topos being repeat, whatever. I mean.
Right. So this this is not locally contractible. So there are various versions of a pro-étale site. The one this one is not locally contractible, right? Because I didn't add all of them. I could have considered the larger one, say even the V site. But this is what I'll do here, and it doesn't matter for the category of pro-étale bundles.
I'm not sure whether my memory is correct. Some vanishing of a higher limb, whatever it is.
Right, so I think here, at least for sheaves like ZP, right, I think for sheaves like the structure sheaf and ZP, if you define them as inverse limit of Z mod P to power n, and here likewise, the higher limb would vanish in this case.
Okay.
I mean, if you'd like, you can replace this by a V site, and the category of vector bundles will be the same in this case. If that's okay. So, right, I have this, and now the key point is that I can still define the notion of Chern classes for this larger category of bundles. So, how do I do that? Well, let me, as we'll do in topology, let me think of a vector bundle as of the data of a map to the classifying space or stack. So if I have a pro-étale bundle, then I can encode this as a map to the pro-étale classifying stack of my group GLN. And here, let me not define rigorously what this is doing. So this is GLN living over QP, and really, this is an algebraic group, but I consider it as an analytic variety. So I take in simplification. And then, well, if you like, you can just define, you can just take this association as the definition of what it means to of this classifying stack. So that maps into it are pro-étale bundles on the source. And now, well, whatever this, so this is a map depending on whatever this is, there should be a, I can pull back cohomology classes. So let me just now use the same numerology as I would use for usual Chern classes, and you'll see in a second why it's justified. So I can go from the étale cohomology of this classifying stack, and in a second I'll tell you how this cohomology looks like. So my discussion will be complete. So well, here I could work even with integral coefficients. So there will be a map to cohomology of my scheme. Okay. Now, what is this gadget? Well, okay, maybe there's some fancy setup here, but whatever this is, since étale cohomology satisfies pro-étale descent, I can compute this using the usual kind of simplicial construction which I use to study cohomology of classifying spaces. So it will be a simplicial space whose a simplicial rigid space whose terms are just products of copies of this group. But now it's it will be expressed in terms of étale cohomology of the identification of an algebraic group. But in p-adic geometry, there is, as in complex geometry, there is an Artin type comparison theorem which relates cohomology of identification to the original algebraic étale cohomology. And so if you unwind this, it will turn out that there is a natural map, which in this case is an isomorphism, from the étale cohomology of the usual algebraic classifying stack. So you prove this. So this is follows from Huber's comparison of cohomology. Okay, but now in this group we have our usual algebraic Chern classes Ci. So I can map them under my classifying map. So Ci maps to something which I'll call Ci of this pro-étale bundle. Okay, and this will be my definition of Chern classes. Right? So the kind of the structural point of this discussion is that I can define Chern classes for this larger category. And well, let's just see what it does on these two classes of examples. But maybe before I do that, are there any questions about the definition? Please.
Why do you use hi-étale instead of hi-pro-étale?
I could have done, yeah. It's since I didn't tell you, it would be more prudent to use pro-étale. So somehow this is ultimately built from cohomology with finite coefficients. Mm-hmm. And I mean, for these gadgets, which are maybe some stacks on pro-étale, in pro-étale topology, you can talk both about pro-étale and étale cohomology, and they're the same with finite coefficients.
Oh, okay.
That's what I'm using here. Yeah. It would be better to use pro-étale, but then I'd have to use that pro-étale and étale cohomology of my x are the same. Yeah, exactly.
Sorry, I'm not familiar with this comparison, but does that work for general and reductive groups?
Yes, absolutely. Yeah.
But how general and all group scheme is not false?
I think it's whatever generality in which Huber's comparison works. I think it works for my understanding. If you have any finite type algebraic, well, yeah. If this underlying space of the group was a finite type algebraic variety, then it would be okay.
Okay.
So the comparison is actually just happening term-wise in this simplicial.
Exactly, right. I mean, actually, all I need for this discussion is just a map, and the map goes in the right direction, actually. But sort of for psychological comfort, that there seem to be no more kind of characteristic classes of pro-étale bundles than there are of étale bundles. Than there are of usual bundles.
Excuse me, in complex solution, you also should make a twisted version for Chern-Simons set.
Right. Or you mean technically? You mean when I define Chern class? Right.
Yeah.
So somehow, I think somehow a more closer analog of this complex story would be local systems with CP coefficients rather than ZP. And I think Dustin has a characteristic class for that. And so my understanding is that since I do ZP coefficients, those state twists got trivialized. This is one, but maybe if you have some other way of thinking about it.
Yeah, that's exactly what I would say.
Okay. Right, but technically, yes, exactly. But now on these Chern classes, the state twists will really appear, and this will be crucial. Okay, so since I claimed that this is a generalization of Chern classes of the usual vector bundles, I should tell you what it does on this category. So let's do two examples. Great. So if you have if you had a usual vector bundle, and you consider the associated pro-étale bundle, then the Chern classes will just be the very same thing. Essentially by functionality of that construction. But now what's more interesting is to look at bundles coming from the right side of this diagram. So let me first do the case of a particular local system, which will be the Tate twist, which already appeared. So let me look at a vector bundle, which is the structure sheaf, multiplied with the local system ZP of 1. Okay, I already used this notation, but let me clarify that this is this is just a local system which records the Galois action on the roots of unity of p power order. And, well, I'll just abbreviate this to OX, twisted by 1. So it's some pro-étale bundle, which really I'm only able to view as a bundle because I adjoined these larger inverse limits of covers. But really, well, I didn't specify what my X is, but this local system, it was pulled back from spectrum of QP. So let me just assume that X here is just a point, spectrum of QP. So what is its Chern class? So it's a line bundle, so its only interesting Chern class is the first one. And so it should live in second cohomology of this X. And now it's crucial that this field is not algebraically closed. And, well, as for any field, its cohomology would be the cohomology of the Galois group. But now it's second cohomology of the p-adic of the Galois group of QP with coefficients twisted by 1. This is exactly the dualizing object for the category of finite dimensional QP representations. Galois representations, and this is canonically identified with ZP by Tate duality. And so this actually goes to 1 under this identification. So in particular, this is definitely not a bundle coming from the usual vector bundles, because of course all the usual vector bundles are trivial on a point, and their Chern classes would be 0. But this one has an interesting Chern class. Right? And now, in the remaining 2 or 3 minutes, the key to understanding this relation between local systems and this bottom side of this formula is to have an analog of, right, so I said that my goal will be to explain why these Lazare classes are secondary to Chern classes. And so let me just explain an analog of this relation, that somehow you can recover Chern classes of bundles associated to local systems from these secondary Chern classes. And so it's true for formal reasons. That if you took for any local system living on X, the ith Chern class of the associated bundle can be expressed in terms of this Lazare class of the local system and another class. So it's a product. So let me explain what this formula means. So this is going to be a rational identity because I only define these Lazare classes rationally. And so this lives in a rational cohomology with coefficients twisted by I. This lives in cohomology in previous degree without any twist. And so this will be a certain class. So for a certain class, kappa I, which does not depend on anything, it's a class chosen once and for all. And it now lives in first cohomology of just the Galois group of the base field with coefficients in the Tate twist. And so now, if I multiply these 2 things together, I indeed get a class in the right group. And the claim is that this identity holds. And so the fact that it holds for some such class, it's kind of a formal thing, which you can prove by contemplating the universal case by comparing cohomology of GLN as an algebraic group and cohomology of GLN ZP as an abstract, profinite group. So what's non-trivial is that this class kappa I is non-zero, and it's I think it's been proven by Annette Huber and Guido Kings. That they actually pin down this class completely. And so it's a certain class and it's a certain class in Galois cohomology. And it's in fact, there's a natural map from QP to this Galois cohomology called the Bloch-Caro exponential map. And which is an isomorphism if I is larger than 1. And this is the image of element 1 under this map. So it's an explicit class, right? And so this is a certain computation in the universal case. So they weren't quite thinking about pro-étale vector bundles. They were rather thinking about regulators in K-theory of ZP. But it turns out that this is the very same computation that you have to do here. And so my time is almost up. So let me just say in words, rather than explain it carefully, what the proof will now be. So here I placed myself in a special situation where I'm trying to compute these Lazare classes in top degree. And it turns out that this situation is one where to compute them, it's enough to compute this product. So this associated Chern class. Because in this situation, multiplying with this Galois cohomology class will not lose any information. I rigged my situation specifically for that. And it turns out that this Chern class I can compute completely because this bundle, now local system might well have been irreducible, but since I now transit with this much larger sheaf, and because of this completion, I have many more sections, which in turn, and it turns out that this local system, sorry, this pro-étale bundle has a filtration whose associated graded pieces are completely understandable, and whose Chern classes I can compute. And this gives me, after I do the algebra, this gives me this formula. Basically, it all comes down to examples of these two types, either bundles coming from usual analytic site or some of these state twists. And sorry, it's probably not very understandable, but my time is up, so let me stop here.
Well, thank you very much. Are there questions?
Yeah. Yeah. I mean, you have p-adic Hilbert correspondence and p-adic Simpson correspondence. How can you see these classes on these correspondences?
Yeah, very good question. So here, kind of the whole point of what I was doing here was that we lived over a non-algebraically closed field. But if you lived over CP, and your variety was smooth proper, then the Chern classes of this pro-étale vector bundle, it will be equal to the Chern class of the associated Higgs bundle under the Simpson correspondence. So by Chern class of the associated Higgs bundle, I just mean the Chern class of the underlying vector bundle. Somehow it follows from, so Ben Hoyer explained to me that under his correspondence, right, it follows directly from his definition of the correspondence. I can tell you the details later.
So very naive question. So primary Chern classes appear in the Riemann formula, right? So are there any Riemann type formulas for these new classes?
So this is a great question. I wish I knew. I know that the Len and Bloch, they have a paper about a Riemann formula for these secondary Chern classes. And I mean, if I'm being very modest, I can think of this formula as some kind of type of Riemann-Roch situation for varieties of local systems of geometric origin. Very special, right? So, I wish I knew yet, I think. If someone knows, actually.
Don't know is the question. So. If somebody knows, they should report.
Yeah, please. Yeah.
Okay. Where does the weighting by M come from?
Right, okay, great. So I didn't really explain this. So it comes from the state twist. So maybe I can just write down one formula on the board. So this pro-étale, I claim that, okay, everything comes down to this pro-étale bundle. And the point is that this pro-étale bundle, it has a filtration with graded pieces, which are graded pieces of this Higgs bundle, but twisted by a Tate twist M. So this is kind of an analog of Hodge-Tate decomposition. If you were over a point, there is the statement that if you take a Galois representation in tensor with CP, it decomposes in terms of Hodge cohomology, but with Tate twists. This is just a family version of that. And now the point is that this Tate twist, it has interesting Chern classes by this computation. And so once you do the algebra, it gives you this weight M in front.
Oh, sorry. Yes. So I wonder whether this statement also holds for example, for some sort of R&B stacks. I mean, over diamonds.
Yeah. Somehow, I don't know what's the definition of a Hodge-Tate local system on such a thing. It's kind of a classical definition that uses smoothness. But if you define a Hodge-Tate local system as the fact that the associated pro-étale bundle has such a filtration, then it would be true anytime.
So the question, is there some kind of global version of this? Like this H1 QP, Q of I for, say, Q or for imaginary quadratic fields has a very simple description.
Sorry, you want to take global? You want to take the global Galois group, or?
Yeah.
Right, so this was somehow what came up here. I mean, in general, I think my understanding is that the dimensions of these global Galois cohomology groups are not completely known, which is that's not known. There's conjectures for what they're equal to.
Yeah, but I meant in the H1. The H1 is pretty well known with Q coefficients, right? Just by Rham.
Sorry. Could you? Sorry. You're doing GLN of Q. Yes. Sorry. I mean, so you don't do the cohomology of the Galois group. You're doing the cohomology of GLN of a field.
No. The H1 with Q of I coefficient, QP of I coefficients. I thought that was just related to the K theory of the field, which.
The
odd K theory of the field.
Yes, H1 of which space?
I'm looking at the theorem of Huber-Kings.
Yes. Right. Yes. Thank you. Yeah. Right.
Global analogs of those, I guess.
Right. So.
I wondered if there was some kind of connection, global version.
Yeah. Yes. This is very good. So right. I wish somehow theoretically you could imagine that there was such a formula in global cohomology, because both that thing and this thing make sense in global cohomology. Right. I don't yet know what this class would be. You can kind of, I think, sorry, if I understand correctly, right, at least I think for some weights, this class does seem to live to global Galois cohomology. I don't know if that's a reasonable. So whenever you have K theory and whenever Z has K theory, maybe divisible by 4.
That's what Snyder's conflicts is.
Right, okay.
But I mean, there's no such thing as the left-hand side still doesn't make sense globally.
Yeah.
Right, but the...
So what is Hodge?
Exactly, so, but say if I had a local system with just of geometric origin, then I could make a ad hoc definition for this value. Okay. And I mean, sort of, Dustin has a result of the form that some torsion characteristic classes of a local system related to, of geometric origin are related to Chern classes of some vector bundle associated to the same motive. So, right, this is a very good question. I wish I knew, but all the actual proofs use p-adic Hodge theories.
Maybe. Also, M times something associated with M in terms of Hodge filtration appears in Kato's canonical heights. Yeah.
Right.
Can you please?
Yeah. So I was curious about that. I don't have anything non-trivial to say. Somehow, actually, my understanding was in Kato's canonical height, there are some kind of other sequences of integers which would also do the job, rather than these weights M. Yeah, they just have to be symmetric. But correct me if I'm wrong. But right, I don't. Yeah, I was curious about it, but I don't have any non-trivial to say. Yeah.
Can you reprove the vanishing statements for variation of structures which are coming from geometry using?
Right. Yes. Yeah, so
places where it's good, like you presented here.
Right, so it's kind of the same type of question. So here, I mean, these classes, the Chern-Simons classes, they come from K theory of C, if you like. Here I have something coming from K theory of QP. And if I had a local system with monodromy in some number field, I think it's the same. What I had in mind was the same type of argument that Dustin, I think, explained last time. But I don't. Right, so I think if I knew that these Lazare classes come from classes in global K theory, there would be a chance of such an argument. But otherwise, just an analogy.
Is this a special case? The quadratic can you do for a finite extension?
Yeah. No, I can't. It's important that it's QP. It's kind of it's a special situation where cupping of this class is a lossless procedure. In general, it would lose some information. I hope that similar formula is true in general, but some additional input is needed to prove it. Yeah, it's special to base B QP.
Okay. No more questions, so we thank the speaker again.